Okay, so next speaker is Robert Luce from Gurobi optimization, and we'll talk about global non-convex optimization using Gurobi.
Well, thanks, Bartolomeo, and thank you very much for giving me the chance for talking in front of such a keen audience. And thanks, Paul. Being an interior point developer myself, your presentation, of course, spoke to my heart. So I'm sure we'll have plenty of time to follow up. But it's time to switch gears now. So goodbye to convex. Now for the next 45 minutes, I want to talk strictly non-convex. And I'll do this from a couple of different angles, so please be prepared for notation switches without notice and stuff I'm sure we'll figure out. But to set the baseline, I want to start with mixed integer quadratically constrained programming. So that's the old world language. It would be optimization in the new world, but yeah, Gurobi was still old world. So we have a quadratic objective, linear or fine constraints, and we have quadratic equalities. So inequalities, bounds and variables, and of course we're Gurobi, so we have integrality constraints on some of the variables. All in all, it's a pretty difficult problem, and all that we require is that the QKs are symmetric, and our ambitious goal is to find a provably global optimal solution, or multiple, if you like it. And we do the one trick we can, which is branch and bound. And I think most of you have heard it, but just to be sure that we all agree on the simplicity of the idea. I've put the whole branch and bound algorithm for mixed integer optimization on one slide. So let's walk quickly through it. So the old trick is integrality constraints are difficult. Let's just ignore them. What remains is now, again, for a short time here, a convex problem, which we just assume to be solvable to optimality, and that solution is X star. And now we're going to check all the variables that are required to take integer values, and if they take by chance integer values from the convex representation, we're done. Otherwise, we would just pick one of the fractional variables and now divide the search space into two subproblems. One, and where we require that this variable must take lower bound on the ceiling of that fractional value, and the other way symmetrically an upper bound on the floor of that. And since xi here, the one we picked, must take integer values, we have systematically subdivided it. We haven't lost anything. And now we will simply recurse on these two subproblems, solve both subproblems to optimality, and whatever we got from comparing these two solutions, we have an globally optimal solution. Great. The little trick that branch and bound will benefit from, if at some point in time we'll just figure out, wow, this is a feasible point, and then we got a solution at hand, even though we haven't proved that this is the globally optimal solution. But we will use the solution to stop our search once the objective value of the subproblem exceeds that of a known solution. So that's a very important thing. And yeah, so if you implement this naively, it may just simply enumerate all integer points. It's an exponential algorithm by nature. In practice, you won't explore subtrees though, and to me, it's every time I look at this description, it's surprising how effective this idea actually is, despite its simplicity. And at the same time, it's worth mentioning, in order to get this from a paper, wow, this is some noise out there. Maybe you can close the doors, I'm not sure. In order to get this into a practical, robust industrial algorithm, it's an insane amount of code you need to write, and an insane amount of tricks you have to invent or pick up from literature to get anywhere with that. All right, that was NIP. Now let's talk about non-convex quadratic constraints, because these are the other nasty things. And here we do a conceptually similar trick as for the integer constraints. We will, in the end, replace the subproblems. We we will craft subproblems that are convex. This will be, again, our workhorse. And to do this, first step is we will break the quadratic constraints into a set of very simple elementary bilinear constraints of the form z equals 2xy. Simplify a little bit here. We will replace these constraints by their convex envelope, and then we will decide to not only branch on these fractional integer variables, but also on those variables that take place in these elementary bilinear constraints. Okay, it sounds like a bit complicated, but it goes all well with an example, so let's just do that. We have this quadratic constraints, 3x squared minus 7x minus 2 and so forth and so forth. And now we look at each individual term there and introduce for each quadratic term an auxiliary variable. So for x1 squared, we just call it z11. For the term x1 times x2, we call it z12 and so forth. Okay, and now let's just pretend that this somehow we can process this. Then we can just rewrite the original quadratic constraint by a simple linear one, by just plugging in the auxiliary variables. Done. All right. Only problem, of course, now, how do we enforce that these auxiliary variables take the value that corresponds to the quadratic terms in the original formulation? Oh, and this is the thing we have to give up. We will not require that this is exactly, that these equalities hold exactly, but instead we will confine, we will increase the feasible space with it and confine the relation of these two to a linear envelope around the feasible set. And you see it like there, so for this elementary constraint x times y equals to z, you need exactly 4 hyperplanes to describe the envelope, 2 for the lower envelope, 2 for the upper envelope. You can already guess that if you don't have like an equality but only inequality, like z is greater or equal than x times y, then you may not need both sides of the envelope, maybe 2 suffice. All right. And now why is this a good idea? So if you look carefully at these hyperplanes we introduced for capturing the linear envelope, the coefficients and the right-hand sides of all the variables involved depend only on the bounds of the problem variables. So this is very nice for integrating it with the convex sub-problem solved, for which we want to have our LP workhorse, the simplex algorithm. So it means we only need to tweak the coefficients and the right-hand sides of the corresponding constraints at each subproblem. The smaller the domains are, the better is the envelope. The smaller is the violation of the bilinear constraints, so branching is an appropriate technique to reduce that. And now you need to answer 2 questions essentially. Which variables do I pick to branch on, and if I've picked such a variable, what is the branching value I should define to define the 2 subproblems? But all of this, I don't think there's some serious math you can put into it. We use a number of heuristic criterions that we combine one way or the other. I don't think there's the absolute solution to that. Okay. So that was the rough walkthrough branch and bound for non-convex quadratic problems. And now I want to speak a little bit to the experts in the room. Maybe Andrea knows all that, so he can go get a coffee. Hopefully not too many others have the same feeling, because now I'm going to talk about a cutting plane that is extremely useful for these linear envelopes for quadratic constraints. And to get this presented in a nice way, I will now simplify the whole problem and denotation a little bit. So I do away with the constraints, and instead I will look only at a non-convex quadratic objective function. It doesn't change anything from the cut mechanics, it just simplifies the way we have to write it down. All right, so we got an indefinite Q, non-convex objective function, and now if we would relax our integrality constraints, that this alone still, as before, doesn't help us. We still would have non-convex continuous problem as subproblems. It's not good. Okay, so we do exactly what I just explained. We will decompose the Q, we will introduce auxiliary variables, and so forth. And here's an extremely condensed but readable way to rewrite that without all the indices in Z and whatever. So you will now have the original problem variables, lowercase x, and the auxiliary variables, uppercase x. And then if you think about the polyhedral constraints that describe the linear hulls, you can see that this is more or less some more linear constraints and extended formulation for this problem. So this is this S. S contains all the McCormick constraints, the envelopes. And we continue to have the property that in the course of branching, we change the local bounds and thus these polyhedral constraints. Okay, but how often will we need to branch in order to truly achieve x times x transpose equals to capital X? This is what we need to satisfy, right? This is what gets, it's not guaranteed unless we branch so much on the auxiliary variables. And now we will do this by a trick called cutting planes. Maybe simplest first, cutting planes just linear constraint that is globally valid for the problem, we can just add, and that will remove stuff from the search space that doesn't contain any feasible points for the original problem. Okay, so F is our feasible set for the original optimization problem, the non-convex one. We have R, this is the feasible set of some relaxation during branch and bound that we are currently looking at. And we have an optimal relaxation solution, X star, in the set of feasible relaxations. But unfortunately, it doesn't add up. So the auxiliary variable does not match the products of the original problem variable. And this is a situation that is bad for us because it means we need to branch more. Branching creates subproblems, eats memory, eats time. So if everything we can do to prevent further branching is welcome means. So what we will do is we will try to find any linear inequality d transpose x plus trace dx less or equal than g. So this is just in generic form to write a linear form here. That's nothing special. But the two properties below. So we want that if I plug in the relaxation solution in this linear equation, it will exceed g. But if I intersect it with the feasible space, nothing is lost. So this was the situation I was alluding to in the beginning. All right, so this is what we need to look for. Then we will just add this linear constraint to the relaxation, which continues to be a linear problem. Right? You can just add a constraint, run simplex again, we'll get a better solution that doesn't have this optimal solution, x star. So we've cut it off. That's the idea. And well, we will derive such a linear equality directly from the equation x transpose equals to capital X. And it's very simple. So this is just some basic linear algebra. So if these are equal, I can throw away one of the two sides of the equality. I can rearrange. I can augment it with a 1, because the 2 block is still positive semi-definite. If the whole thing is positive semi-definite, I can apply a congruence to the left and right, which doesn't change the inertia. And then finally, I get the equation that I'm really interested in, which is the last one. So 0 is less or equal than this augmented matrix 1x capital X. And that one is important enough to deserve its own letter. So this is x hat from now. So this is the relation I want to use to produce cuts from. And if I look at the variational characterization of that, it means that x hat is positive semi-definite if and only f. For all vectors multiplied from left and right, I end up on the right half line. And so if I have a solution x star from the relaxation, I can see that this is cut off by the linear cutting plane v transpose x hat v greater or equal to 0. Whenever I have a vector v, that actually brings me back to the left half line at the point of the relaxation solution. Well, we all know what that means. We just need an eigenvector or anything in the eigenspace relating to some negative eigenvalues. All right, and that's what we will do. So if I have a normalized eigenpair for a negative eigenvalue, we can just compute the thing. The violation of this inequality will be just exactly that eigenvalue. Or more generally, if I have a whole subspace generated from eigenvectors from negative eigenvalues, then any point in that linear space gives me a valid cut. And it's also the other way around. So if you give me some cut for this for this construction, it must have some weight if I project it down into the subspace. And yeah, so then you can play around. You can do all the linear algebra places. But the bottom line is you need U. U is exactly that subspace that's spanned by all the eigenvectors in the negative eigenvalues. Right. So this is our search space for cutting planes from now on. Issue with that is slightly expensive to compute for larger n, and also what simplex really doesn't like if you feed it a lot of non-zero values into the basis matrix. Then all the linear algebra slows down, and suddenly your previously very efficient subproblem solves become quite expensive. So we have to balance it one way or the other. Okay, so and here's the very basic trick to avoid that. So whenever you have any subset of your variables, I, and you look at the induced submatrix from X hat, well, then you have at least a handle on the size, on the density of cut that gets out of it. What you give up is just by standard variational principles from diagnosis. You just give up a little bit of strength of the cut. How much? Well, you can characterize that further by more Fisher theorems and what you have. Anyway, these are the techniques to restrict attention to a smaller subspace. All right. Then there's another problem that you will have to address, because typically, if you look at about typical non-convex quadratic function, there's no reason to believe that this will be a dense matrix, right? Why should it? So, but in turn, this means for the auxiliary variables, if you look at the relation of these x times x transpose and capital X, there just won't be all variables in there. So here's one thing to get away from these sorrows. So you just pick any clique of what you find in Q and use that in the first place as a candidate to produce cuts. So you pick a clique in Q, you apply the whole cut heuristic just to the graph induced by that clique. And simple heuristic 2, well, you just compute a chordal completion of your graph. And then, I mean, that was also, thanks Paul, that was on your slides. I mean, you didn't emphasize it, but with a chordal graph, what you don't get in general is that you can enumerate actually the maximal cliques. That's very special about chordal graphs. There are at most m of them. And now these are then the starting points for your cut producer. And then you will get some holds from your chordal completion, and these unfortunately, in the cut you will just have to fill in by some valid upper bound in the variable, so that something that doesn't cut off something accidentally, but you can do it. It's still, if it still cuts off the relaxation solution, it's good to go. All right, and here's the most fancy device, which we haven't implemented in Gurobi, but I played around with it when I looked into it, and found it interesting, so I thought I'd share it here. Now, if you think about a non-convex or an indefinite Q that is largely sparse, even the eigenspace information becomes a little bit difficult to obtain here, actually. So, and then you resort to standard linear algebra tools to get an approximation to this subspace that brings you to the left half line. And typical algorithms, Lanczos or Krutoff-Schur algorithms. These are typically then matrix vector-based algorithms, so quite fast. And if it converges, which bit subtle here, then you still get a basis matrix. Not really basis matrix. You get some vectors that span an interesting space, that lie in the target space. But certificates become a bit weaker. And once you have that from this procedure, You can either go with your dense cuts as before, or now you take the U and project that again on a smaller support. And there are again heuristics for that. And anyway, I think you could do a whole research project just on how to generate the best possible cuts from this procedure. But yeah, I didn't do that. All right, so that concludes the little technical part on these cutting planes. And now I want to show you a small application of all this non-convex effort. I mean, we have to get the merit somewhere. I mean, our customers, they get merit too, but we as the researchers, we also want to have some merit from the work we put into this non-convex business here. So here's my pocket toy. It's non-negative matrix factorization. So NMF is a structured low-rank matrix factorization. So you're given some matrix X with entries in the non-negative orthant. You get a target factorization rank R, and you need to find W and H low-rank matrices, each again entry-wise non-negative, so that X is reproduced by the factorization W times H, or approximated, or whatever game you want to play with that. They're everything's allowed. And why? So if you haven't seen this before, so why is this interesting? I mean, it's just another way to play the lower rank factorization game, right? So if you instead of putting entry-wise non-negativity constraints, you can put orthogonality constraints, and you get like SED, PCA-like kind of things, or if you put any other manifold constraint, that you end up another geometry. This is just a different geometry which has surprisingly interesting properties. So I think what made it big in the early 2000s, or where it got first attention, was if you have like a set of a database of phase pictures, and you do a non-negative matrix factorization from that, you can interpret somehow the factors. So in that case, the columns of the H matrix would show you facial features like this is a nose, this is different types of mouth, this is ears, this is eyebrows. So somehow it helps to interpret the data to features. So there's a bunch of literature on that. But I'm not talking about the applications here. I'm talking about a very intricate question that is the uniqueness of non-negative matrix factorizations. So first of all, I mean, you can always permute rows and columns of W and H. So that's a kind of, when I talk about uniqueness, modulo that. And you can also always apply actually positive diagonal scaling. Positive diagonal scaling D to W and H, and that will, of course, also not change the results. So modulo these two things. So the question is this a unique factorization modulo these two properties or not? And yeah, it's one of the questions that is just as hard to answer the original one. What is the factorization? But there are fun things they're going on in the geometry here. And so here's one condition that makes life easy. It's the so-called sufficiently scattered condition. So a little bit of notation, the cone of H is the one generated by the columns of H, then the dual cone just is a dual cone. Since it's polyhedral, there's no surprise in there. But then you have C. C is a bit interesting kind of a cone, it's a second order cone, that geometry is so that there's a certain minimum expansion happening in this cone, and the dual cone is quite a big one then. Okay, so, but the conditions that are interesting. So if the C is part of cone H, so if the columns of H have intrinsically a little bit of expansion, or intrinsically an intrinsic sparsity somewhere. That is what it means as a C1. And if the extreme points of the dual cone of C are exactly the ones where the dual cone of H and the boundary match, then you have this beautiful theorem that if this is the case for both W and H, then this NMF is unique up to permutation scaling. And now the question is, how do you ever in life check these two conditions? And there is finally where I can circle back on non-convex quadratic optimization. Because as it turns out, the computational procedure, well, the best computational procedure we know so far is you maximize the two norms subject to polyhedral constraints. And of course, that's a non-convex problem, right? minimizing would be easy, but here you really have to maximize, and then you have to look at the solutions. Actually, you have to look at the set of all optimal solutions. And this is another difficult problem, right? If you generally give me all the optimal solutions, but here you know a priori, if these conditions are fulfilled, they are exactly R, and they have a special form. So, and this is something that you can check with our solver framework we've implemented in Gurobi. So that was a big win for me to see that it's even useful for our little kind of toy research problem here. All right, that concludes the non-convex quadratic part. And now I'm going to step a little bit away from quadratic straight to general nonlinear in branch and bound. So that's the next step in line. So let's look at that constraint. So f of theta is equal to that. So who knows that expression? I think it ought to be the length of the Archimedean spiral, but I'm not so entirely sure anymore. Anyway, so if for some reason you would like to have this as a constraint in your global optimization problem, you would write it down that way. But so how can we repeat this as we did for the non-convex quadratic one? We still need to come back to this property of efficiently solvable convex subproblems. We still need these convergence when I subdivide the envelopes and stuff. So can we repeat all this for such complicated constraints? And it turns out, yes, somewhat. So the first step here is to take this nonlinear constraint and decompose it into a set of atomic nonlinear constraints, each of the form yk equals to fk of x, and fk is then one of the atomic functions that you typically would have, like trigonometric functions, power functions, square root, and so forth. And then, instead of trying to convexify such bilinear constraints as we did like half an hour ago with z equals to x times y, we will replace the epigraph of these atomic constraints by a convex envelope, and then we do the thing that we can do, which is branching until the relaxation is good enough for our purpose. So again, we do it by example. So let's take this constraint. We introduce now auxiliary variables y1, y2, y3, and y4. So first one is just quadratic equality constraint. It's a univariate here, so that's extremely simple, luckily, but that's not guaranteed, of course. Then we have a square root, a linear constraint, and a logarithmic constraint. Okay, very good. And finally, with all these auxiliaries, we can replace the original constraint on theta using y2 and y4. Great. So problem solved. Now we again have the problem. We need to enforce the connection of the yk variables to the atomic nonlinear constraints on the right-hand side. And well, we do what we always do. You know, find the convex relaxation to the epigraph. We do so. And now this is an implementation detail. This you can do it differently if you think it's better, but we felt we go that way. We always do with a fixed number of hyperplanes, say 6 or whatever the number is in the end, just to keep the complexity. If you think about how to implement such a thing, and then all the way through branch and bound, the number of constraints change in the subproblems, it's going to be a big mess. So let's make it 6. Okay. And then maybe we don't always need upper and lower envelopes. That again depends a little bit on the sense of the nonlinear constraint. Is it equality, less or equal, greater or equal? But the underlying principle that is branching on X reduces the domain, promotes feasibility of the relaxation and so forth. That still is an effect. But the hyperplane generation now is quite complicated, because essentially for every atomic nonlinear constraint, you have to explicitly find a way, what is the best way to compute convex envelopes. So for every atom you support, you need to think a little bit on how to do this. And but the effect is now, if you think about it a bit more broadly, so you have atomic functions, and you're dynamically adjusting envelopes throughout the tree search in the decomposition algorithm. It is conceptually similar to having a dynamically adapted piecewise linear approximation of these atomic nonlinear constraints throughout in the branching bound solve. Right, so this is pretty heavy, and I spare you the details on that. So just some picks to convince you that this is about right. So here's the sine function. This is blue. And the interval, so the domain of x is indicated by this black bar on the bottom. It's lower bound to the left and upper bound to the right. And x is the argument of the sine function here. All right. So for the upper envelope, we have very little choice, right? So we just, it's effectively the only sensible way to compute an upper envelope is to take the secant through f of lower bound and f of upper bound, and there's no way we can do any better with that. And then the lower envelope, well, that's easier. So that's similar as you would do it for a convex function that you try to auto-approximate. You just take tangents at some points. Of course, now the magic is which points. And yeah, again, we have some heuristic that does it in a sensible way. Maybe not the best, but does something that is kind of right. And then what you end up with, if you do this procedure, is the whole region shaded in red. That's the feasible set, and you see that's a lot of points that we will have to get rid of during branching and with cutting planes. But yeah, that's as good as it gets for a very simple relaxation. Of course, you could refine the lower envelope a little bit more by let's not use 2, let's use 3, 4, 5, 6, or however you like tangents. But in the end, there will still be a lot to chew away. It doesn't get prettier if the domain of x has convex and concave parts. Then essentially this is close to useless, not entirely, but close to useless relaxation. But hopefully branching will fix it over time, right? But so let's see how we do it. So the lower envelope, I've put down the formula there. You can just compute. This is just given by leftmost solution to the point at which we want to take a tangent, and the rest is just then secant or another tangent. It's the same for the upper envelope. So it's just, I don't know, hacking away on that. Yeah, and here, I mean, this is where you have to give up entirely. So nothing to gain. Here you can only do blind search during branching bound until you have chopped up the domain of x sufficiently to get into convex or concave parts. Another nasty case, x to the power of -2. What can you do? If you have no bounds on x, you can do exactly nothing. The best relaxation for that is, well, y is greater or equal than 0. Great. So that also requires intervention of branching early on to govern. Even if you slice away some part of the domain, it still doesn't look so nice. And the biggest problem, of course, is the pole in the middle. So if you do branching on that domain, you may want to reduce the pole as soon as possible to get into some convex or concave subdomain. But as soon as you're there, it goes quickly then. Then you know the typical tricks, using a secant as upper bound and tangent as lower bound. And then there are some numerical things that you have to look at it. Because even if technically the pole is no longer the domain, being close to the pole doesn't help either. Okay, good. Yeah, and this is the picture that should still motivate us all to say this is not total crap. It actually works. So, and why does it work? The convergence of this linear hull to the epigraph actually is quite good. It's pointwise, it's very convergent. If you do a sensible branching scheme, you have to be a bit more careful, but we have experts in the team who know all the details on that. So yeah, so there's convergence to the epigraph, and it's not as bad as you could fear. Okay, so I walked you now very quickly through all the efforts we've made in respect to global non-convex optimization in the last 3 to 4 years. So the history is that in Gurobi 9 we extended our branching bound to non-convex quadratic functions. In 9 and 10 we also introduced like a static piecewise linear approximation to nonlinear atomic functions. And we also used the original formulation actually in some heuristics, most notably in some nonlinear interior point method to produce primal feasible solutions. Then in 11, we did a big step forward. Now it implements effectively what I've just shown you, this dynamic handling of the convex hulls and the branching with that. The only downside, it wasn't really user-friendly, because if you think about going to a customer and explain, yeah, you have to formulate your constraints using these auxiliary variables, it's probably not going to be appreciated. So people tend to want to write down what the function is. So, but we're on track. So hopefully by end of this year, we will have a more general framework than accept any multivariate nonlinear constraint, and we will figure out the decomposition and auxiliary variables that you would need or not need ourselves. So that's on track. And we will still use then the full nonlinear multivariate constraint again in our continuous nonlinear backend somehow. Okay, that brings me directly to my second little toy problem. So thank you, Andrea. So Andrea has actually explained everything I have to say here, but you know, as for students, repeating doesn't hurt. So here's one way to write down an optimization problem. So we minimize, we have input variables x and output variables y. And we want to minimize some objective function that where the input and the output enter. And we have the property that the input and output are connected linearly. So ax equal y. That's a pretty typical situation in many settings. And then, of course, if you have bounds, integrality, sure thing, we can handle it on the way. Fine. But now let's replace this A instead by a trained predictor. Right? So same thinking applies. You have an input and output, and the predictor says how these two we have to relate. And wouldn't it be great if you could just put this information into your global optimization problem? Well, that's what Andrea explained. This is the package actually he mentioned earlier this morning. So it's Gurobi machine learning. It is a Python package. There are others, right? There's Omelette, and there are two more that I don't recall at this point. But this is our that specifically works best for Gurobi, I would say. So it's a Python package to formulate a trained predictor directly into a Gurobi model. And depending on the predictor, I mean, there are so many nonlinear functions that people like to play with. We had the relu function galore this morning, but I think the second most interesting for us currently is logistic function as activators. So that is also something we support in that package. So if you have network based on logistic functions, then you can put it in, and we will figure out a useful formulation in terms of a constraint for optimization model. Right. So and how and here's one thing that we noticed while working on Gurobi 11. So that's why also I showed you the history. So in Gurobi 10, we had these logistic regression models solved by a static piecewise linear approximation. And up front, we computed just a couple of segments, and that was it. And with 11, we switched to this dynamic thing, and we also had a nonlinear interior point method to produce our solutions, and made a big difference. So both in terms of the solution quality you get from the dynamic handling of the relaxation, and in terms of the solution time, it was quite amazing. And well, for softmax and the adversarial ML model that Andrea alluded to was also quite motivating for us. So I invite you also, if you have a fun problem where you could, wow, I would like to put in this trend predictor as a constraint, just try it. It's fun stuff. Right, and of course this is just the next step then. So the way Gurobi machine learning currently works, it takes the regressor and now spells out all the intermediates down to the atomic function level, as I did in the example. That's not optimal for us, because it takes away our abilities to prune nodes, like Andrea showed. So if we then in Gurobi 12 get the whole network as one thing, as one constraint, we have a much higher chance to get some meaningful pre-processing, because pre-solve is essential for most problem skills we learned. Yeah, so this is something we're looking forward to. And hopefully we will also better solutions are generated from the interior point methods in our product. We'll see. All right. So maybe to wrap up, non-convex global optimization is fun. I hope I could convey that message. If there's anything, that's what I wanted for you to take away. And if you're coming from the MIP camp and you have a running branch and bound, it's quite a journey to get that thing transformed into something that supports spatial branch and bound and has all the little details that come up in the difference between a linear relaxation versus a spatial relaxation. And I think what's the motivation a little bit for us developers is that the overarching question, so if you think back to the 90s, 2000s, MIP was a success story, right? So I think before people also say, yeah, it's mixed optimization, it's really hard, global optimization, how would you do this? And now it's a commodity tool. It's used throughout, everywhere. And if there's a slim chance that we can do something similar for non-convex optimization on that level, that would be pretty cool. And that's part of the motivation here. All right, thanks.